We continue our discussion of homological algebra, and today the topic is going to be the Hom tensor adjunction. So to fix the setting, let's say that R denotes a not necessarily commutative ring, and M is supposed to be a right R module, while N is a left R module. And finally, we fix just some abelian group and call it X. And now the first definition is that a map from the Cartesian product of M and N going to our fixed abelian group. So right now this is just a map of sets, and we now require something about that map. Such a map is called R-balanced. And that's the definition, so let's put it in green. It's called R-balanced if it satisfies the following three properties. Namely, firstly, we want it to be bilinear. I mean, that's already two properties, so we want it to be linear in the first and in the second variable. So this G means what it always means. Fm and n plus n prime is equal to Fm comma n plus Fm comma n prime. Second, the same thing for the other variables. So f of m plus m prime comma n should equal f of m comma n plus f of m prime comma n. Yeah, so the usual additivity in both variables. And finally, this is probably name giving for this term R-balanced, is the following compatibility with the multiplication by ring elements. Namely, if we take some element R from our ring and multiply it to an element M in our right R module, so I've got to multiply it from the right like this. And then we apply the map F for such a pair, M times R comma N. Then this is supposed to be the same thing as if we had multiplied the other variable, which now is multiplication from the left, since N was supposed to be a left R module. And then I want to end up at the same element via F. Yeah, so these three conditions define what an R-balanced map is. Yeah, sort of a bi-additive map with this additional compatibility with the ring multiplication. And of course, this is required to hold true for all M and n prime in M, n and n prime in N, and all ring elements R in R. Okay, and now the definition of tensor product of those two modules, the right R module M and the left R module N, should be thought of as the most general way of constructing such an R-balanced map. And most general means in the sense that every other such R-balanced map actually will factorize over this most general R-balanced map. So this is captured by the following definition. The tensor product of M and N over R is first of all just an abelian group, like the one that was called X before. So it's an abelian group which now goes by the name M tensor N. So M tensor, and we put down in the notation the ring R here also. Together with an R-balanced map going into that abelian group, And this map is also usually just denoted tensor. So this is now going from the product of M times N into this abelian group, M tensor Rn. And now we need to convey this idea that it is the most general way of coming up with such an R-balanced map. And this, of course, means it satisfies a universal property. So it is such an R-balanced map which satisfies the following universal property. So such that the following universal property holds. So I've got here my R-balanced map M tensor n, M times n, denoted by tensor going into this abelian group. And like I said, if you have any other such R-balanced map, so starting at M times n, call it F, going to some abelian group X, then it uniquely factorizes over this tensor product, over this most general one, meaning I've got a unique arrow in this direction, which makes this triangle commute. So there exists one and only one map, call it F twiddle, such that the composition of tensor and F twiddle is equal to M. And since last time we had the situation that we did not require uniqueness, so let's make sure that the universal property is completely clear, and let's phrase it in words again. So what this diagram says is that for every R-balanced map, F from M times n to X, there exists a unique homomorphism of abelian groups. So call it F twiddle from M tensor Rn going to X, such that F is just the composition of first tensors, then F twiddle, so F twiddle composed with tensor. So maybe key in this definition is to not only think about the tensor product as some object here, some abelian group that arises out of this module, but it's better to think about it really in the way that it's this whole map here. So this map tensor going from the product into this abelian group, which has this universal property. I mean, I said this is a definition, yeah, so I better now verify that actually such a tensor product does exist, yeah. I mean, right now we just said it is something which has this universal property. This needs verification that this is a non-empty definition, so such a tensor product exists. So how do we do this? I mean, if we want to construct an abelian group together with an R-balanced map from the product M times n into this abelian group, which has this universal property, that then sort of it must be defined in a canonical way. Yeah, there cannot be any choices or so. So what's the best canonical way to construct a map from M times n into an abelian group? Well, what we would do is we take first of all the free abelian group on this set M times n. Yeah, sort of this is the most canonical way to come up with a free abelian group out of this data M and n. And now this is good because we already have a canonical map from the product into this free abelian group just as the inclusion of the basis. Yeah, I can just map any pair M comma n into this free abelian group just as the corresponding basis element in here. And now I want that this inclusion of the basis becomes actually an R universal map with our definition made above. And right now, if I just include m times n into this free abelian group, this will not be satisfied. I will not have the required relations 1, 2, 3 from up there. So what I do is I simply enforce them. Yeah? So every of the 3 requirements up there gives me a relation when I want that the inclusion of m times n satisfies these 3 points, and I just make them true in this module, meaning I factor out the subgroup generated by those relations. So let U be the subgroup of this free abelian group. Generated by the following elements. So first of all, I want the inclusion to require number 1. So this is just saying that if I have a pair of the form n comma, no, my left variable is m, right? So m comma n plus n prime, then I want this to be the same as m comma n plus m comma n prime. So I want that this difference here is 0. Yeah? And let me just indicate dot, 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 dot. So I do this with all 3 relations from above. Yeah? I want that the inclusion satisfies these relations. So I just subtract the right-hand side from the left-hand side. And now I'll mod out the subgroup generated by those elements in here, which makes sure that these elements become 0 in the quotient, meaning that this relation is satisfied. So this is for all m prime in m, n prime in n, and let me just move over all r in r. Yeah, these ring elements will become relevant in the third relation. Okay, so let U be the subgroup generated by all those elements, and then I simply set our abelian group M tensor Rn to be our free abelian group on this product set m times n, and now I mod out this subgroup U to make sure the above relation hold for the inclusion map of m times n. Yeah, and then, like I said, the map from m times n, so to m tensor Rn, this is just going to be take an element m, I apply it tensor n. So this means just plugging in the pair m comma n into this map tensor. Yeah, this is the notation for this, and I just define this now as the representative of this pair m n within this quotient here above. Yeah, so completely canonical, and by definition, sort of by construction of the subgroup U, this becomes now an R-balanced map. To see that with this stipulations, this actually does become a tensor product, meaning it satisfies the universal property, let's check how we do that. So if we are now given some map F from m comma n to x, which is R-balanced, then I can say that the map F twiddle, which is required to exist and to be unique by the universal property, I just do it like this. So every element in this tensor product can be written as some sum of images under this canonical map tensor. So I can always write it as m tensor n. Yeah? So every element is, of course, an integral linear combination of those basis elements, and these coefficients, I can also just put them inside the 2 factors here, and therefore every element is of this form, but it's not uniquely so. Yeah, so that's something one has to keep in mind. So every element in this group here is a sum of those images of elements m tensor n here, so of those so-called elementary tensors, but not uniquely so. But still, I get a well-defined assignment if I just say that I map this to the sum of f of m comma n. Yeah? So why is this well-defined? That's well-defined because I can get from one presentation as such a sum of elementary tensors to another by applying these three relations I've just factored out. So I can just add those elements here to go from one presentation to another. But if I then apply f to such an element, it becomes 0. Yeah? So it doesn't change the sum here. And therefore, I get a well-defined element here in the group X. And second important remark is that this construction is actually functorial. So what do I mean by this? I mean by this that if I fix, say, a right R module M, then I want M tensor R to be a functor from left R modules to abelian groups. Yeah? If I just plug in the left R module on the right-hand side here. And if I define the tensor product in this way, then I can simply check that this will commute with homomorphisms between those left R modules. So this is definitely going to be a functor, and the same goes the other way around. Yeah? So if I fix the module n and I make this the variable, then I will also get a functor. Yeah? And I think that's sort of important, because if you just define it by the universal property, then, well, what you will get is you will get objects which are unique up to unique isomorphism. Yeah? This is the usual general nonsense. But nevertheless, if you want a functor, then you really need to get an object, and not an isomorphism class of objects. Yeah? You really need, so given m and n, you really want an object. And this construction yields one. Yeah? So this is why it's important to note at this point that this is functorial, and I should say it's functorial in both variables. Yeah? So in n and m.
One is reminded of homology. You define homology by this huge complex, and something similar is going on here, right? You have this free abelian group on m times n, which is usually infinite, or in many important cases, even uncountable. And then you divide out some huge submodule, and we will see that very often this will give you something small, although this definition is very big. And the example of homology might also warn you that this is important to see the functoriality, but might not be the best way to actually compute a tensor product.
Right. I mean, you know probably the situation already from vector spaces. If you have seen this construction before there, then you would know that if those are finite dimensional vector spaces, then this new vector space will actually have dimension of m, and the dimension will be the dimension of m times the dimension of n. And that's just because if you pick a basis in m and pick a basis in n, then you can just take the pairwise elementary tensors of those basis elements, and these will span the whole space. Yeah? And this looks like a more efficient construction, and well, it is in terms of how large are the objects which you have to handle, but it's not a functorial construction, yeah, because you pick bases and you're not allowed to do any picking when you want to come up with a functor. Yeah? So that's why even in the vector space case, an analog construction to this one is the way to go. Now, the only problem right now is that the tensor product, as just defined, is only an abelian group. Yeah? And typically, we want to come up with R modules again. Yeah? So if we have a tensor product of modules, you want to get a module again. But if you have non-commutative rings, one has to be a little more careful about this, because what one then actually needs as input for the tensor product are so-called bimodules. So let me define what those are. So if I want to define a bimodule, I need to have two rings available, so call the second one S. So R-S are supposed to be rings. And then we define an R-S-bimodule as, well, again, an abelian group, which then comes with actions of R and S from left and right. So it's an abelian group, first of all, call it M, which in itself is a left R module and a right S module, which is a left R module and a right S module. And at this point, the definition is not quite over yet, because we still need to require some compatibility about those two multiplications. Namely, they're supposed to be associative, meaning it's a left and a right module, such that we have that if I first multiply multiply from the left with an element R from the ring R, and afterwards I multiply from the right with an element S from the ring S. And that's supposed to be the same thing as if I had first multiplied from right with S and then from left with R. Yeah, so this associativity should hold in a bimodule. Okay, so it's a very natural definition. And let's look at some examples as usual when we introduce a new object. So whenever I have some ring R, then I can take the n-fold product of this ring, and this then becomes an MNR, so the matrix algebra of n by n matrices with entries in R from the left and an R module from the right, so an MNR R bimodule. Yeah, so I can think of elements in R to the n as just n tuples of elements in the ring R, and I can multiply such a vector, if you want, such an n tuple of ring elements R from left with a matrix. So I get another n tuple, and I can, of course, also multiply those n tuples diagonally in all entries from the right, and then this equality here is satisfied, yeah, with this associativity. So this is an example of a bimodule. And yet another example is whenever R is actually a commutative ring. Then it's fair to say that this distinction between left and R modules does not really matter, because every left R module is canonically also an RR bimodule, and every right R module is canonically an RR bimodule. And how does this work? Let's just do the case that M is a right R module. M is an RR bimodule. Namely, well, I have already defined the right, or I have already available the right action with elements of R, so I need to define what the left multiplication is, and I just define it as I multiply an element M now from the left with R, just by saying, well, that's the same thing as if I had multiplied with this element from the right. And now to have this associativity that's required already for left R modules, yeah, if you multiply with the product of rings elements from the left, then it shouldn't matter if I first multiply the ring elements or I first multiply with the module element and afterwards again with the other ring element. To make this this equality, this identity true in this ring, I need the commutativity here now, yeah, because I will need to swap the order of the two elements if I multiply from the right. So therefore, it's important here that this construction only works for commutative rings. And of course, well, the same thing works the other way around. Yeah, if M is a left R module, then I take the right-hand side of as what I want to define, and I take the left-hand side as a definition. Okay, and finally, if R is not necessarily commutative, and I just have a left R module M, then the one thing I at least can always do is I can consider this left R module M as an RZ bimodule. So I can still multiply with elements from the ring of integers from the right. So then M is an RZ bimodule. Because, well, the bimodule property I need to verify is the following one. So if I have R times M and now I multiply with an integer k from the right-hand side, well, what does this even mean? I, of course, define the multiplication of the integers on the right-hand side in the only possible way. When I write M times k, I mean I add M k times, right? So this is just M plus da 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 plus M k times. And in case k is negative, then I would take minus signs in front of everything here. And now I have the module property of this left R module here, which says I have this distributivity, that this is the same thing as just R times M plus da 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 plus R times M. And this, of course, now is just k times the summand r times m. So this is the same thing as if I had first multiplied r times m and afterwards multiplied by k. Yeah, so it's immediate that this bimodule property is actually satisfied. So I can consider every left R module as an RZ bimodule. And of course, the very same argument, yeah, mutatis mutandis, says that
or something like that.
yes, that right R module is canonically a ZR bimodule. Yeah. All right. So why am I telling you about those bimodules? This is because, remember, our tensor product of a right R module with a left R module is just an abelian group as of now, and I want to turn this now into a module again if the input modules are bimodules. So let's put down how that works. So in case B is an R-S module, an R-S bimodule, and say, first case, that A is a right R module, then I can take my abelian group, which is given by the tensor product, A tensor RB. Yeah, I mean, an RS bimodule is in particular a left R module. Yeah, if I just forget about the multiplication with S from the right. So I end up here with an abelian group, but now on this abelian group I can define my right S module structure by using the right S module structure on B. So this is a right S module. And it is so in the only possible way it can be. So if I have an elementary tensor, yeah, remember every element in the tensor product is a sum of those elementary tensors. So it's always enough to declare what the action is on an elementary tensor. And I have such an elementary tensor and I multiply with an element S from the ring S from the right. Then I just want this to be the elementary tensor, a tensor B times S. Yeah, and this gives me a well-defined right action with the ring S. And the similar case is now in case we have a right S module C. Whoops, that's badly written. Right S module. Then I can do the following. So for the tensor product, I have the situation that I could turn the abelian group into a right S module. And now remember, the video is called the Tensor-hom adjunction. So the corresponding or dual statement is for the Hom functor. I can define now a right R module structure on the Hom sets from B to C. So this is the following statement. Then the homomorphisms, so the right S module homomorphisms from B to C. Yeah, so B is an RS bimodule. I consider it as a right S module here. First of all, I forget about the left action by R. Then I consider the set of homomorphisms from B to C, which commute with the right action by S. And this is then a right S module. Is a right R module. Never mind. So what's left in the bimodule B is still the left R action, and I can use this to declare a right R module structure on the Hom set. And I do so as follows. So if I have a homomorphism F from B to C, and I want to multiply it now from right with an element R from the ring R, then I can declare the new homomorphism that comes out here just by saying pointwise what it is. Namely, if I apply this new homomorphism to an element B of B, then I want this to be just F of R times B. Yeah? And now you should convince yourself that this actually does define a right R module structure on this Hom set. And well, the reason is that, formally we have just switched parentheses here. Yeah? So if you multiply with the product R1 times R2 here, then we would have R1 times R2 here, and you can just change parentheses to make this requirement of right multiplication module work. So this gives the right R module structure on the Hom set, as well as before we had the right S module structure on the tensor product. And now it turns out that these two constructions, the tensor product and the Hom functors, are adjoints of one another. So this is the so-called Tensor-hom adjunction. And we formulate this as a theorem. The functors, first of all, blank tensor RB. Yeah, so B is still a left R module and a right S module. So this is a functor going from, now I need a right R module here, so it's going from mod R. Yeah, I mean, I think the notation is suggestive. If a left module was, the category of left modules was R mod, then of course the category of right modules is mod R. And given such an right R module M, I can plug it in here. I get an abelian group, which by the bimodule structure of B still has a right S action, so I end up in mod S. So I get a functor from right R modules to right S modules, and the Hom set gives me a functor in the other direction. So the S module homomorphisms from B comma blank, so to some fixed right S module, not to some fixed, to some variable right S module, that gives me a functor from the category of right S modules. And well, if I plug in such a right S module here, I just told you above that I come up with a left R module structure, excuse me, with a right R module structure on this Hom set. So this goes to mod R. It is confusing, yeah. Okay, so this is the good thing, that's what we need. So these two functors go into opposite directions, so they have a chance to be adjoint functors of one another, and they actually are. Yeah, so these are the functors, this and this are adjoint. So let's put down the Hom set adjunction to make sure we understand what this means. So we fix now some right R module A, so some object in this first category of right R modules. And we fix another object C in this other category of right S modules. And then we have a natural isomorphism between the Hom sets. So we have a natural isomorphism from Hom S of the tensor product A tensor RB into C. And this natural isomorphism now goes into the Hom set over R, it should be now, from A comma, and now I put in the S homomorphisms from B to C. Yeah, so let's make sure that we did no mistake here. A was a right R module. I can form the tensor product with a left R module. B is a left R module, but at the same time a right S module, and therefore I've got a right S module action on this tensor product. C was by definition a right S module, so I can consider the S module homomorphisms here, so it looks correct. And on the other side, A was supposed to be a right R module. B is considered here as a right S module, and so is C. And since B still has this left R action, I get a right R module structure on the Hom set, so I can consider homomorphism of right R modules on the right-hand side, and this also works. So these two are adjoints of one another, but one way of showing that is actually to use the universal property. Yeah, so if one does it the right way, then one will see that this right Hom set here just describes those R-balanced maps. Yeah, so these two homomorphism requirements give you the two additivities, and yeah, well, if you do the details, you'll see that every R-balanced map then factorizes over a map through this tensor product. This is one way of proving it, but actually I find this more complicated than doing it directly, so I prefer to do it just directly, meaning we just put down this isomorphism and its inverse. So let me just say that one can do it, and then we do it directly. So either use the, and yeah, I should say the new universal property. so the original universal property was still the one dealing with abelian groups in the target, but now when we have those bimodules, then one can make this universal property work with R-module homomorphisms. Yeah? So then the requirement is not that there exists a unique map of abelian groups, but actually a unique homomorphism of modules. And with this new universal property, one can prove the statement. Or what we will do is we make the natural isomorphism explicit. So, and its inverse explicit. Namely in one direction, so say from left to right. So if I have here an right S-module homomorphism G from the right S-module A tensor R B going into C, and I take such a homomorphism and I want to come up with a homomorphism here on the right-hand side. So that means I need to say what does it do on an element A. And on an element A, I need to get a homomorphism from B to C. So what does this homomorphism do on an element B? Well, it does now the only thing that you can do. I just put both into G. So G of A comma B. Yeah, then I end up in an element C as I should here. And so as you can see, there was simply no other way than defining it like this. And the same goes for the inverse. So let's try it the other way around. Okay, so let me bring it back into light again. So I now start with a homomorphism F from the right R module A into the right R module of homomorphisms from B to C. So that's F going from A to hom R or hom S. Yes, hom S. From B to C. And I need to come up with a homomorphism defined here, like here on the tensor product and going to C. So I need to say what it does on an elementary tensor. That's always enough. And it does the following. Well, I plug in A into F. So then I come up with a homomorphism from B to C, and then I can still plug in B. And then I end up in C, as I should here, yeah, as I should on the left-hand side. Right. And now it's a simple check that these two constructions are inverses of one another, and they will also be natural, yeah, because the commutativity with morphisms must work if they are defined in this completely canonical way. So there's no way they won't be natural, and doing it is cumbersome, but yeah, not really helpful. So this concludes the proof of the Hom tensor adjunction, and in the next video we will see what it's good for.